And welcome back. Time has come for us to look at another polar function and then showcase a lot of polar functions. Polar functions are insanely powerful and also visually amazing and also very complicated to deal with unless you have a graphing tool. So what we're going to do for the most part with these is not that much, honestly. Polar coordinates are going to be something we can handle by hand. Converting polar functions and polar equations into rectangular is something we can do by hand. But unless we get some lovely contrived polar functions, they're going to get out of hand very, very quickly. And you'll see what I mean here in a bit. But for now, let's just look at a very basic polar function. R of theta is equal to theta. Compare this to f of x is equal to x, or y equal x. Right? If that was your identity function in rectangular systems, maybe this might be contrived to be an identity function in polar systems. It's not, because it's not going to be anything remotely as useful or as important, but it is still something we can handle. So r equal to theta. That's our guy. So when r is 0, theta is 0. When theta is pi, r is pi, about 3.1. When theta is pi over 2, which is about 1.5, r is about 1.5. When r is about pi over 4, which is about 0.7, 0.8, r is about that same value. So pi over 4, go about there, we'll say. And then when r is 2 pi, which is about 6, theta is about that same value. So I kind of have a point out that way, which I can't reach. When r is 3 pi over 2, that's about 4.5, I'm guessing. So let's kind of slide this around a little bit. Oh, I regret everything. Can't do that. So that would put our point kind of down there-ish. And so altogether, that gives us a graph looking something like that. It's a spiral. It's a spiral. Sorry. I can't draw it. But yeah, you recognize then that r equal theta looks like a spiral graph. A little spiral thing. Because when r is 0, theta is 0. When r is pi over 2, theta is pi over 2. When r is pi, theta is pi. When r is 2 pi, and 4 pi, and 6 pi, and 8 pi, and so on. And this keeps going on and on. And actually, you see on Desmos the maximum number of r and theta values it will generate for you. It stops at around, what is this? 2, 4, 6, 8, 10, about 12 pi. It'll do about 12 pi. And also, it will not plot negative values of theta. So the true solutions to the function there, or the equation, is actually both of these things put together. So that's fun, right? That is the identity function, if you could call it that, for polar systems. And don't call it that. No one calls it that, because it's not really as useful as the identity function is y equal x. But we do kind of have a fun thing going on here, a little yin and yang kind of situation that never truly quite ends, but hey. But we know how to make them, and we know what they look like. And that's really all I want us to get out of this video. So we're just going to kind of have some fun with what these things look like. And I want to show just how quickly out of hand these things get. So r equal cosine theta, that's something you can figure out by plotting points pretty quickly, right? When theta is 0, cosine is 1. When theta is pi over 2, cosine is 0. When theta is pi over 4, cosine is root 2, which corresponds about there. When theta is pi over 6, it's about root 3 over 2. And at pi over 3, it's at 1/2, which is what we expect. And then for sine, we actually get this circle up there, which again makes sense. Because when theta is pi over 2, we're at 1. When theta is at 0, we're at 0. At pi over 6, we do hit that 1/2 point. At pi over 3, we're at root 3 over 2. And we can work our way around again. But that's pretty much where the magic ends. What if I went from sine of 2 theta, from sine theta to sine of 2 theta? Well, yeah, as you guessed, we get a 4-leaf clover. And yes, you can plot this out by hand. The way it works, as I recall, is you start here and it works over and down and then around and then around and around. And that's how it goes. It just goes in that pattern over and over again. And you can track that by plotting points. You have to use some very not nice angles. I mean, you can do pi over 12 and that sort of thing, but I think you need more than that to really nail down this behavior. But yeah, that's sine 2 theta. Cosine 2 theta is another 4-leaf clover, just oriented differently. And you would expect maybe 3 theta to be a 6-leaf clover, but no, hilariously enough, that's a 3-leaf clover. And that has a little bit, I think, to do with the double angle formula, something like that. But that's a reason that we will never probably really get into in this course. Just want to show that, hey, you can make very pretty graphs. And I don't even want to consider what rectangular equation would be required to make this sort of thing. I don't even want to consider it. I'm sure there is one, and I'm sure it's ugly as sin. But compare that to cosine 3 theta. Very short, very to the point, and something we can plot points on very quickly, especially if you have a program or a calculator at our hand, just to throw in values of theta into this equation, get our values out, and make our graphs. Alright, but enough about that. Let's get a little weird. 1 plus cosine of theta plus pi over 2. Now, if this were y equal 1 plus cosine of x plus pi over 2, right, that's a cosine wave shifted up by 1, shifted to the right by pi over 2, we can handle those transformations. We can't really handle those transformations in this course. Well, I mean, we can, just not in this coordinate system. Yeah, to the surprise of everyone, the circle that we had before, cosine theta, when we do just a little bit of changes, we actually get this heart shape going on. I think it's called a cardioid, not that that matters. And these previous shapes were called roses, not that that matters. But just a little bit of change can make a huge difference in the world of polar functions. 5 cosine of pi over 2 over theta looks like that guy right there. A very intricate rose. More of a spiral graph, to be honest with you. And actually, this thing right here stops at the 16 pi over 2 limit. It never actually loops back on itself. It actually would take up the whole circle. So that's fun too. We also have a cardioid that's folded in on itself. That has a fancy term as well. I forget them because they don't really matter. And then if we get really fancy pants, we can make a parabola. Wait, what? Yeah, we can make a parabola. Right, r is x squared plus y squared, square rooted. You can actually convert any rectangular equation or any rectangular function into polar functions just by doing the appropriate conversions. So this thing right here is simply just a parabola. And you can convert that back, right? You have r cosine theta squared equal to sine theta, multiply both sides by r, and you've got now x squared is equal to y. And then we can kind of make this amoeba-looking thing, right? Just showing just how weird this stuff gets. Doesn't take that much effort to make it weird. That's one way to do it. You can still plot points on this thing. Just throw in values of theta, get r values out, plot your polar coordinates, and you would get this lemniscate, I think they're called. And then just a few more. You can make a cardioid that's folded on itself 3 times. And you can make a polar rose that's folded in on itself. Right, this is now a rose with another rose inside of it. There's no real limit to what you can do with these things. Okay, there is a limit to what you can do with them. But more to the point, there is a much higher limit of what you can do to these compared to the limit you had with rectangular functions. All these things I just showed you, they are functions now. And once you get into calculus, that's going to fill you with a mild bit of dread. Because the things that you can do in calculus with functions start to go crazy. Right? You can find the area inside this thing. This is not Calc 1, but still later you can find the areas, you can find the lengths, you can find perimeters. You can do all those things. You can find these roots, right, where they hit the x and y axes. You can do all sorts of crazy stuff with these things. And I just wanted to show you for now that you know how to make them by hand, by plotting points, and you know what they represent. That as theta moves, r moves. And that's really all I want us to be able to do with this stuff right now. Can we make a sketch of a graph of a function that is polar using values of theta that we choose? And we're going to work with simple ones by hand because, yeah, they get pretty complicated pretty fast, as it turns out. And so I just want us to hypothesize, plot points, and do kind of a heuristic approach to this stuff. That's really all I want us to get out of this. Kind of have our eyes filled with wonder, as it were. So I hope that has happened for you, and I will see you in the classes and videos to come. We have reached the end for polar coordinates and polar systems. Just hopefully persuaded you that, yeah, they are very powerful. And then in the next few videos, we will round out the course with parametric systems and parametric equations. So I look forward to it. I do really look forward to it. I will see you up ahead.